My name's Drew Marty Carina. I'm here from John Deere, and I'm introducing our keynote speaker, John Mueller. John has been with Deere for 18 years. He's an engineering leader in the space of developing our onboard operating systems and our developer toolkits that enable our developers to create the cool, useful tools that are empowering our farmers across the world. That John has been highlighted as a leader in this space, both in the developing of the operating systems as well as in enabling AI and creating better systems to help us collect the data necessary for those aspirations. In addition to his technical accomplishments and contributions, he's been highlighted by his coworkers as being a nice, chill guy to work with, and that is an actual quote. And so with that, please introduce John Mueller.
Thanks, Drew. Appreciate it. I didn't know what he was going to say there, so most of that is true. So, thanks. So again, my name's John Mueller. I'm with John Deere. I'm an engineering leader in the precision technology space, and I'm just super thankful and grateful to be able to give you a talk today on unpacking the impact of technology and AI, and the impact that that's had over the last 2 decades, 3 decades in agriculture. And so. Thanks to NC State, thanks to Danny and the organizers for having us here. I'm very honored and humbled to be here. I'm going to talk about a couple of things. One of the first things I'm going to talk about is some of the challenges that farmers face today. And a lot of these have been talked about already, so they're going to sound a little bit familiar, but we're going to reiterate that farmers are facing some significant challenges. And we've gone through periods in the past where technology has been able to drastically increase the productivity and profitability of farmers. And we're going to talk a little bit about why we're in another period of that. And spoiler alert, it has to do with AI. So one of the most significant challenges that we face as a global population and that we face as humanity, and that really get passed down to farmers, is that our global population is expected to continue to increase at least for the next 25 years or so. And this comes with significant challenges. One of those being that there isn't, at least in the US, and this is true for many countries across the globe too, there isn't any more land with which to produce that food. And in fact, in a lot of cases, the amount of arable land in a lot of countries is shrinking. And so with that global population growth, it's actually expected that the increase in food demand will be on the order of 50%. You can look at those numbers and be like, wait a minute, 8 to 10 billion and a 50% increase in food demand, what gives? That math doesn't math too well. But as countries develop, as populations develop, they are shifting towards a more nutrient-rich diet, more animal-based diet, and it just takes more production and more food output to keep up with that population development as well as the population growth. And so not only is it an 8 to 10 billion person problem, it's a 50% increase in food demand over the next 25 years with not much more land, in fact, less land in a lot of countries. So how do we solve this problem? How do farmers keep up with population growth? And the answer comes with, obviously, technology. Another challenge that farmers face, and this is especially true in a lot of the row crops, a lot of my examples today will be row crop or orchard crop focused, is that timing is incredibly important in producing a profitable crop. So there's generally 2 time windows in a year that are really critical around that planting and around that harvest time. And a lot has to go right during those windows of time, or else you begin to lose yield potential, you begin to lose productivity, you begin to lose profitability. The soil has to be just the right temperature, and the crop, to get to full maturity, needs the right amount of heat days. And so those windows are shrinking. It's generally, for corn in the US, it's generally about a 2-week optimal window between when the soil temperature is right and the risk is removed of that soil temperature falling too low again, and when the crops need to be in the ground to get their maximum yield potential. And then similarly in the harvest, it's once that grain is dried down to the right point, you don't want to take it out too wet, you don't want to take it out too dry. You generally have just a few weeks, maybe a little bit longer than planting, to get that out of the field. And then in between there's a whole host of things that can go terribly wrong. So farmers have, once their seed is in the ground, once their crop is in the ground, they have very little control over a whole lot of variables. There's some that they have some control over, but they can't control how many heat days end up being in a certain area. They can't control the weather in a certain area. They can maybe control disease and pest if they can identify it early enough, if they can detect it and mitigate it early enough. But there's a whole host of things that can go wrong that generally only take away from their yield and take away from their profitability as the season matures. The other big challenge is a decreasing labor pool. And so the average farmer in the US is 55 years old. They're generally working from 12 to 18 hours a day. And this is really provides an unsustainable situation for them. Here's just some trends as to the percentage of populations in a couple of different countries that are involved in the food production. And so in the US today, less than 2% of the population is involved in food production. And so this is an incredible challenge for farmers. Labor is very scarce. So you have these short planting windows, you have these seasons where you have very little control over the variables. You need more people to get more things done with less, and you just don't have those people. And with other countries, we see that as well. I mean, just going back to, in the grand scheme of things, 1840 is recent history where over 60% of the population was involved in food production, and now we're at 2%. So this is a very significant challenge for farmers. Farmers are pretty amazing people. Every day they have to wear many hats. They're entrepreneurs, they're operations managers, they're agronomists, they're data scientists, they're engineers, and they're mechanics. And that's just over the course of a single spring day like what we're seeing today. So today, there's millions of farmers that are wearing every single one of those hats that I just mentioned. And so they need the ability to perform their operation and to execute their function in a way that removes cognitive load and removes burden from that. And you guessed it, technology is the way that we've been doing that and continue to do that. Farming at scale is not like gardening in your garden. I garden, I generally grow about 10 to 15 tomato plants and 10 cucumber plants. I like making salsa and pickles and stuff like that. Farming at scale is much different than that. It's like outdoor manufacturing. And so if you can imagine outdoor manufacturing at scale, can you imagine like a car assembly line being done outside? It's sometimes not going to turn out too well. But in the US, there's 10 trillion corn and soybean seeds planted every year. And so there's an incredible amount that's on the line here. And each plant, so you say, how can you manage the profitability and the yield of 10 trillion plants? Each plant has to be managed individually and given the best opportunities to succeed in order for us to achieve the goal of keeping up with the increased food demand over the next 25 years. Farmers get one chance a year to get it right. So they don't have, unlike us in technology, us in academia, we love doing research, we love doing experiments, we love formulating hypotheses, knowing that they may be wrong in the end, but still doing the experiments anyways. Farmers don't always get the luxury to just hypothesize and run experiments. They need to know that what they're gonna do in their field is gonna work and it's gonna work well. Over the lifetime, a farmer may get 40 chances to get it right. And pass down and create a sustainable operation and a sustainable legacy for the next generation of farmers. So every season, every crop rotation, every decision is on the line. The way that we solve this is through technology, and John Deere is not new in our technology journey. We have been innovating. Innovation is actually one of our core values of our company, and we've been doing that from the very beginning. It started in 1837, so like 139 years ago or whatever that is, with a person that came from the East Coast with his plow and moved to the Midwest and saw like this plow does not work in the Midwest. These soils have way too much clay. The soils doesn't fall off the plow. And so what are we going to do about it? We're going to innovate. We're going to come up with a better way of doing it. We're going to develop a better plow that removes the dirt as it's going through the prairie soil. In 1918, we made another huge bet in technology by going from horsepower to horsepower, by buying a tractor company. This was very controversial at the time, actually. People were like, what do you mean you're going to take a horse off the farm and stop pulling a plow, right? And so we made a big bet as a company to say, hey, tractors are probably the future in farming. And so I think it was a good bet. And then today, just a couple years ago at CES, and again last year at CES, we've started to unveil our next generation of fully autonomous equipment that have been built on really 2.5 decades of technology development. And so I want to walk you through that technology development journey. This is kind of another view of how productivity has evolved, or thinking about productivity has evolved over the last even 50 years. So in 1950, it was all about horsepower. How can I get more power into my tractor so that I can pull bigger implements so that I can get more done in a day? In the 70s, it came to comfort. How do I allow myself to spend more hours in the field? Now I have the horsepower. Now I need to spend just more hours in the field getting more done in a day. And then it moved into kind of like the space age or the satellite age with GPS guidance. That allowed us to do things precisely, to use less inputs. And then with our digital platforms, allowed us to really start to analyze data better, to offboard data better. I think of this as kind of our information age of evolution. And then came AI precision automation in the mid-teens. And so this really said, hey, these technologies are getting good enough to now we can actually have the machine make some of our decisions for us, and it's going to do just as good of a job, if not a better job, than I can do myself. And even if it can't make a better decision than I can maybe make once, when I'm sitting there for 18 hours and I've got a million things on my brain, over the course of that day, it's going to do a better job than I can do. And then today we're at level 5 autonomy, fully unsupervised autonomous machines. So at John Deere, we pride ourselves in making very smart, very efficient machines that make our customers more profitable, more sustainable, and more efficient. We like to say it's 35 tons of technology. And one of our strengths in our strategy is our deep vertical integration. So we do everything from the sensor to the software running on the embedded controller to the embedded controller hardware itself, the data all the way up through our displays and our telematics devices, our data platform, and then the tools that we develop to allow customers to analyze their data. So deep vertical integration is a strong point of ours. This is just a quick little snapshot of what our machines, like the technology that maybe existed on our machines in 2009. So 25 or so computers, controllers, 4 million lines of code. We used compact flashcards and USB drives. We had 3 communication buses, quite a few sensors, a GPS receiver. If you fast forward today, this has increased in complexity and increased in technology significantly. We have more than, on a tractor planter system, we have more than 250 controllers now. We have 20 million plus lines of John Deere written code on those machines. We have, over 60 in some cases plus communication networks where all the computers are communicating with each other, and continue to add new sensors and new technologies and new sensor modalities every year. Okay, so what I want to walk you through now is a little bit of tech strategy. This is how John Deere today views our technology strategy, and how do we meet the needs of these farmers through valuable products that increase efficiency and productivity. And really what we aim to do is become the operating system of the farm, right? If you think of a farm, you think of John Deere equipment, at least I do. And so we want to be the operating system on the farm. We want our software and our technology in every machine, regardless of whether it's a green machine or not. We want our technology in everybody's pocket on their phone. We want our applications installed, and we want our ecosystem to be the ecosystem that farmers think about when it's, how do I manage my farm? And then through that foundation, then we will continue to create value that really allows farmers to do unmatched job execution. And so how this looks is it's sort of a technology pyramid. At the bottom, you have the foundational technology, and I'm going to spend some time talking about that. And the thesis here is that as you move up the pyramid, the things that are in the higher tiers are built on the foundation of the lower tiers. So let's start to go through that. First thing I'm going to do is I'm going to talk about our foundational technologies. So from the very beginning of precision farming and our precision technology journey, precise sensing of where we are on Earth, our geospatial location, has been fundamental. We began working with NASA and the Department of Defense in the 90s to figure out how do we use this new technology called GPS to provide accurate positioning to the point where it's usable by farmers. And so we partnered with them, and then we also in 1999 acquired a SATCOM company, and now we operate our own set of satellites that provide a correction signal to the inaccuracies that the GPS system has. And so that satellite network we call the Starfire network, and it operates in the geostationary orbit. The good thing about geostationary is it's so far away that with 6 satellites, we can have redundant coverage of the whole Earth at all times. And so we can provide our customers with a correction signal to GPS that gives them precise location. So let's talk about that a little bit. So if you think about your cell phone, you know, that gets GPS. GPS is gotten a lot better. It's accurate usually within about 3 meters. So think of a kind of a 3 meter, the size of this stage type of thing, accuracy. That's not quite good enough for farmers that need to do precise placement of nutrients, that need to do precision guidance. And so our correction signal, our Starfire signal, can get us down to a 2.5 centimeter position on Earth. So inch or sub-inch accuracy with some of our solutions. And so this is foundational to everything we do. And it really started in the late 90s and early 2000s. So we've been doing precise placement on Earth for 25 plus years. What we can then build on top of that are solutions that help farmers be more productive and with less inputs, and just feel better at the end of the day. And so products like AutoTrack have been in our portfolio for a very long time. This is the machine's ability to drive itself. You know, we like to joke that there's a lot of autonomous companies out there doing great things. John Deere's been hands-free driving for 25 plus years now with this technology. What it also allows us to do is know where the machine is so that we know how to control the machine to reduce inputs. So you can see here our section control takes the inputs right up to the rows without any overlap, without any gap, without any wasted space, without any reduced input or wasted input costs. And then really what this allows us to do also is it allows us to precisely document everything we do on the machine. So we can gather hundreds and even thousands of parameters about the operation and geospatially reconcile those on Earth and have a very accurate record about where did this work occur and what work occurred. When you start to combine that with connectivity then, and that takes multiple forms. For many years, it's been cellular connectivity as we've moved from 2G to 3G to 4G and 5G. More and more machines have become connected. And then most recently, our JD Link Boost product offering uses satellite communications based and gets internet broadband onto the machine. And so this really solves a big challenge that we've had. Cellular networks have been evolving, they've been emerging, but still, even in rural US, but especially in rural other countries, cellular connectivity is not great. And so how do we connect farmers in rural areas even better is satellite communications. And so this really unlocks the tech stack. This allows not only the data that we documented and gathered on board to make its way up, but it allows insights to be generated using our tools and our data platform. It also allows those insights to be brought down back to the machine so that in the field we can make better decisions, whether they're logistics decisions, whether they're agronomic decisions, or whatever it may be. So John Deere now has 1 million connected machines. We just crossed that milestone recently. And so this is an incredible opportunity, right? We all know that data is the fuel for technology, and especially data is the fuel for AI. And we now have 1 million machines that are in the world and connected. What this chart shows is that over time. And you can see the kind of the cyclicality within each year. December 31st tends to be a pretty low day in terms of the amount of connected machines. But you can see on during the peak seasons, in any given day, there could be up to 600,000 machines that are actively sending data to our data platform. What this has resulted in is we now have nearly 500 million acres of data in our data platform. And so we literally have millions and millions of examples of how farming is done in the real world with real machines and real farmers. And so this is an incredible opportunity then for what comes next, which is how do we build the next set of technology solutions on top of that? So at the foundation, it all starts with positioning, starts with guidance, connectivity, and documentation. And then all of that monitoring can occur on the machine. The data can be sent up and it can be into our data platform. And then we build tools on top of that where growers can analyze their data, they can plan their work, they can make decisions that are for the next pass in their field. Maybe it's a spraying pass that were informed by the activities that occurred during planting. So they can make in-season decisions based off the analysis of that data. This is just a couple of screenshots of our operations center. This is a screenshot of a customer planning their work. They have their fields. They know what they're going to plant. They can create plans and work plans with rates. They can send that down to the machine. This is an example of once the data from that job step is in the data platform, how it can be used to do analysis. You can overlay different data layers together and do multivariate analysis and things like that. So moving up that technology pyramid then is advanced technology. So once we have those foundational elements in place on a machine, now we can start to do more advanced technology on that machine. And really this comes in the form of like, how do we make machines do more precise and more automation on the machine in order to improve job quality and job execution? So I'm going to give you maybe one example of what I'm talking about here. So back to kind of a planting system, so a tractor and a planter, guided by GPS, using auto-track to precision guide, and then executed by our robotic row units called ExactEmerge. We now have up to 54 individual electrified robots on a planter. So each one of these row units, we call them, is its own robot that is sensing seeds. It's actuating, and it's doing a pretty incredible job at precisely placing those seeds. So at full scale, we're planting somewhere on the order of 40 up to 100 seeds per second. So if you can think about 40 or 100 times per second, there's seeds going into the ground at highly precise placement. So this is a little bit of a video. It starts with the clear the path down there and works its way clockwise. So a planter has to, with high precision and at high speed, be able to clear the path where the trench is going to be made. It needs to create the trench. It needs to place the seed at an optimal spacing and an optimal depth. It needs to place the fertilizer, and it does that right on top of the seed. And then it needs to close the trench. And then our monitoring systems are gathering data about each one of these rows and each one of these seeds and transmitting that to the data platform so that it can be used and analyzed in Operations Center. We can also, with our mobile apps, do live monitoring of the job. So if you're a farm manager and you have multiple planters running or multiple farms, you can now see, hey, here's how far I'm done. This person stopped. I need to go take a look. I need to send this person to this field next, that type of thing. All right, now for the fun part. So at the top of this pyramid is where AI comes into play. And it comes into play in kind of the sense and act space and autonomy space. So a couple of things that I want to go over in this space. I want to talk a little bit about like what are the key technologies that have changed that make for this physical AI and this AI transformation, what makes it really viable. The first is GPU capabilities. We're all kind of aware, I'm not an AI expert, I'm not an AI engineer at least, But what I know is that GPU capabilities have been the thing that has like really unlocked a lot of the ability to get greater and greater performance out of our precision technology. And so more cores, more ability to do parallelization of inference and model training. The next one is around model architectures. So if you think back, even like 15 years ago, a lot of the more advanced algorithms that were on machines were still kind of linear and nonlinear regression type of algorithms. They were traditional algorithms. And then eventually GPUs became accessible to the point where we could start doing more convolutional neural net, deep learning models, mainly in the area of perception. And we could start to create models with millions of parameters, which is incredible. Those models can do a lot compared to what the standard and linear algorithms can do. Those convolutional neural nets, as powerful as they are, and they're still being applied heavily, take a lot of data and a lot of data labeling and a lot of data scrubbing and then a lot of like supervised learning time. So as good as those are, they still are very manually intensive, I would say, to create. And then in 2017, 8 Google researchers released a paper called "Attention is All That Is Needed" and brought us the transformer model. And this is kind of what's changed everything. It's been the thing that then researchers have taken and thrown the whole internet at it because you can parallelize it, you can train on unsupervised data, and out emerge things like GPT and Sonnet and Opus. And now we're in this new world of large language models and what they can do to help us. And so TBD on like how big these things get, TBD on how useful they become, and TBD when they become like the most relevant that they can. But what we know is that it isn't just going to change agriculture, it literally is changing all of our lives. So another thing that has changed over time that allow us to make this AI transformation in the physical AI space. So 10 years ago, we were able to process an image images that were small, that were grainy, and we could do those at about 1 to 2 frames per second. And now we can, at 15 frames per second, we can process very high definition images with onboard compute. So we don't need to stream video offboard, process it, send results back. We have onboard compute that can do this, and we have many of those computers on board. What that really adds up to is like per pixel or per unit resolution, we are at 1% of the cost of image processing that we were 10 years ago. So this is a huge change in being able to implement CVML technologies. This next one is LiDAR. So we feel that LiDAR is probably a foundational technology that will be incorporated and continue to be incorporated in more and more highly automated and autonomous machines. I'm a fan of Clayton Christensen and classical disruption curves and stuff like that. I take a look at this and I'm like, that does not follow that at all. In this, like each generation of technology from its beginning has leapfrogged the previous technology. So this is really interesting that it doesn't even follow kind of classical disruption. That's how fast it's moving. And then radar is another one. So being able to have multimodal sensing of what's in front of you, perception, LiDAR, radar, and being able to make the best decisions and put together the right technology solutions using those 3 sensor modes. So what does this all add up to? So we have new sensor technology that's maturing very fast. We have 1 million connected machines. We have 500 million acres in our data platform. And we have onboard compute that we can scale, and that's incredibly high powered. What it adds up to is there's going to be a lot of neural nets, and they're going to help us do a lot of things, right? And so I want to give you a few examples of that. The first example I want to highlight is See and Spray. So See and Spray was released a few years ago now into production, and there's now thousands of See and Spray machines in the market. What See and Spray is it's a technology that employs kind of all that that I just mentioned: computer vision, machine learning, edge computing, robotics, algorithms, and ruggedized components, both compute and cameras. It puts that all on a machine and says, hey, well, I'm going through the machine through the field at 15 miles an hour with a 40-meter boom. I'm going to detect the difference between a crop and a weed, and I'm only going to actuate the sprayer when there's a weed. And so this is pretty incredible. Here it is in action. The reason I have an affinity to this solution is several of my teams were among the many teams that helped bring this solution to production a couple years ago. This is an incredible machine. It works very well, and depending on the weed pressure and depending on the crop type and stuff, can give quite a bit of savings, up to 66-70% chemical savings throughout the course of a field. So really impressive solution. The next example is harvest automation. Again, using that same technology stack, CVML, ruggedized compute, cameras on board, it's able to look ahead of the combine, take a look at the crop, figure out like, hey, how dense is this crop? Is it standing or is it laying? And it's able to adjust many parameters on the combine to optimize that job for that crop that's right in front of the combine. So another really great example of using physical AI and neural nets to make job execution better, to take cognitive load off of farmers and make them more productive and more profitable. And then next is our autonomous machines. You're going to see two examples. This one is an autonomous tillage machine that we unveiled a couple years ago in the late stages of development. And then this one is a fully autonomous orchard tractor pulling a blast sprayer that's in kind of the early stages of development. 1 week ago today, I was in an orchard in Fresno, California. Probably that orchard. It's kind of hard to tell. They all look kind of the same. But looking at that machine, it's really incredible how far that has come in just a couple of years, really, and how performant it is. So what's our next opportunity? The next opportunity that's ahead of us, right? So if you think about the data in the data platform, if you think about Operations Center as our ecosystem and our suite of tools that help farmers be more productive, how do we bring LLMs into that to turbocharge it, right? And so this is really the next opportunity, is how do we use LLMs, how do we use agents to give farmers better insights as to their data, to give them insights as to the conditions of their field, the optimal way to plant their field. And so in this example, it's kind of doing a chat, but it's chatting with like help documentation, right? And so it's like, okay, this is neat. I'm asking it how to set up a field. It's going and looking at the help documentation and telling me that. But what if the question that I asked could be on the order of, hey, tell me when it is the right day to go plant that field to get optimal yield. Or tell me what variety of seed I should be using next year in order to optimize for yield in my area. Or tell me about how much chemical I should put on in these zones. That's a whole different question to be asking an LLM, right? It takes a lot of context. This context is what we are starting to call the language of farming, right? What can we use customers' data plus the LLMs? What kind of insights and what kind of decisions can we help farmers make to make them more productive? So we talked a lot about some of this, and so the AI technology stack from kind of digital AI to physical AI includes algorithms, it includes data, it includes compute. And if you think about it, there's lots of companies out there that are doing one or a couple of these, right? So algorithms, you have OpenAI, you have Anthropic. Data, Facebook, Google. Compute, this is Amazon and others. And so we, at John Deere, we also have all three of these, and we have the unique ability to have a fleet of machines and a fleet of connected machines. And so really in this physical AI space, that's where the algorithms, the data, and the compute really come together, enabled by connected machines to turn digital intelligence into like real physical outcomes. And so that's what our technology strategy at John Deere is kind of all about. So how do we then ensure that these products that we build are good? How do we ensure that the AI systems are doing the right thing? This is the big challenge. How do we know that this is going to help a farmer and it's going to help them every day, and they're not going to have to worry about it? this is still the area that there's a lot of work to do in, right? So we're moving from deterministic algorithms to more probabilistic algorithms. And even though Gen AI is still probabilistic, it's more on the order now of like non-deterministic. Like I'm going to get a pretty different answer every time I ask it a question. And so how does that fit into a farmer who needs to know that and have confidence and trust in a system to give them the right answer? This is just a LinkedIn post from last month. A farmer, is it perfect? No. Is it good enough to drive better questions, to drive better decisions and better conversations? Yes. And so that's at least the approach we take at first here is we need to help them understand the limitations of these systems, but we also need to show them the value proposition of that. And so a lot of times with the AI systems that are continuing to get better, the value proposition of what they can provide, the insights that it can provide, the decisions that it can enable are actually greater than the non-determinism of the answer, right? And it's a matter of, hey, let's make sure we're checking the answer. Here's something that I want to leave you with. There was an article that was posted, I think it was in Fortune magazine and maybe LinkedIn a couple months ago. It's called Something Big is Happening. And really it was one person's perspective on like, here's what this means for all of us. And there was a couple of key takeaways for me. One is that we should be using AI tools every day. If we're not using AI tools every day, these are the ones that we have access to and that relate to our professions, whether that's software development, whether that's legal, whether that's supply chain management. We need to be using AI tools every day. If we don't, we're likely to fall behind in our professions. The second takeaway is that we likely should be using like the paid versions of these tools. So a lot of times there's the free versions and they can give you a quick answer. It's usually a shallower answer. But if you use the paid version of these and you really challenge those deeper models to go to work for you, and you challenge them with like, here's the problem I need to solve, then you can really start to test like the boundaries of where it's at today. The other takeaway from this article is that the questions that were asked, these tools are getting so much better so fast that the question we ask today that we say, oh, that's not the right answer, AI can't do this, or a lot of times I hear like, we already tried that. We tried that 5 years ago. We tried that 2 months ago. Those types of answers are no longer valid with AI. It's getting so good so fast that if you're saying, I tried that 2 months ago, or I tried asking AI 2 months ago and it didn't give me the right answer, you're likely behind. Try asking it again. And so just some food for thought. I wanted to leave you there. And I think we have maybe 2 minutes here for some questions.
Howdy. My name is Yuri Kaleo from Texas A&M University, and I also work with Extension. Working with the producers, although we see all this development technology you mentioned about, I also see some producers, they are increasing the frustration with John Deere, and they ask questions to us, and I'm gonna ask you to see your perspective. A lot of them say, I'm paying big amount of money for this technology. For you to have 1 million machines talking to each other, 500 million acres. But we pay big sums of money for these machines, and looks like we actually rent them, and you take the data to price these machines, take more money out of me, and not only that, you bring these machines to our competitors down in South America to compete with us. And they got more frustrated with that. So I would like to hear from you if there is any plan, for example, for John Deere to pay for data, for example, and where is the ethical part and how you think about this and how I can answer the producers that increasing this frustration with your company.
Yeah, it's a fair question. So two things maybe. So with every product that we develop, if it doesn't add value to a grower's farm, if it doesn't meet the expectation, then it's not going to get purchased. And so, so I would say it is fully on us to create products that are valuable, that have good product market fit, that are priced right based off of the value it provides. And then on the data side, we take a lot of care to ensure that the customer's data is customer controlled, right? And that they own the data. They can choose to allow us to use it. They can choose to allow us to learn from it. They can also choose not to allow us to do that. And we take that responsibility very, very seriously. And so that quick answers to both of those questions, but it is on us to create products that customers find valuable, and we take the responsibility of data and data control very, very seriously. Thank you.